So what we're gonna do today is application of Moore circle by considering multiple loadings, and the example problems we're gonna consider are these three cases. First, we'll discuss about pressure vessel problem. Second, we'll discuss about beam and shaft problem, and third, we'll consider pressure vessel problem, which is internal gas with external loading. There can be axial loading and twist or bending in addition to internal pressure. So this analysis will be quite complex. So let's begin from the first problem, pressure vessel problem. So here the geometry that we could consider is following. We'll consider a cylindrical pressure vessel, and this vessel is made out of welded structure. So when you have very long film, such as a long piece of the paper, and if you try to twist this like this, you can see you can somehow make a cylindrical shape out of this twisting this long film. Okay, and if it's like a thin metal sheet instead of a paper sheet, what you can do is you can add some hits at this joint and try to have a welding joint. And in Korea, it's so-called 용접부, and welding joint is typically is weaker than this regular material because there can be some defect and irregularity in the thickness. So the mechanical stability of this structure should be determined by the material property or strength at this welding joint region. Okay, so here the problem gives us some information. The angle that this welding joint make with the vertical line is 20 degree, which is gonna give us some idea on how much we rotate the Moore circle after constructing the Moore circle. Then the problem also gives us some geometry. Radius of 2 meter, so this is 2 meter, and thickness is 1 centimeter. So you can see that thickness is much smaller than radius, which is almost 1/200. So you can consider this as like a thin pressure vessel problem, such that you don't need to worry about the radial direction pressure. And the pressure of gas is given at 0.5 for first few problems. So the problem asks three questions. First, what is the normal stress perpendicular to the welding joint? What is the normal stress perpendicular to the welding joint? Because this should be compared with the normal strength of the welding joint. Second question asks us shear stress parallel to welding joint. What will be the shear stress parallel to welding joint? Okay, and as a third question, instead of asking us some question, the problem gives us the allowable shear stress and allowable normal stress for the welding joint, and ask how much pressure can we give given this kind of limitation in material strength. Okay, so all of these three problems is quite plausible example problems in realistic engineering application. So let's solve the first two problems: normal stress perpendicular to the welding joint and shear stress parallel to the welding joint. Okay, so in previous lecture we discussed about how to obtain the stress state in cylindrical pressure vessel. So when we take axis as x and y, x-axis is along the longitudinal direction, y-axis is along the hoop direction, then what we can do is we can obtain the pressure along x and y direction quite easily using the equation we derived, PR over 2t and PR over t for sigma x and sigma y respectively. And then because the problem is asking us the normal stress perpendicular to welding joint, we can take x prime axis as perpendicular direction to here. We can take y prime axis that is parallel to this welding joint, so that this x prime is rotation about 20 degree from the original xy coordinate system. Now, given this information, what you can do is we can first construct a Moore circle out of xy coordinate reading, and then we rotate the xy in Moore circle by 2 times theta, which is 40 degree counterclockwise, to get the stress value along x prime and y prime direction. Okay, so x prime sigma x prime and tau x prime y prime will be the answers for A and B problem. Now, so let's try to draw the Mohr circle. The average normal stress, if you plug in the numbers, sigma x will be 50 megapascal, sigma y will be 100 megapascal. Average of this is 75 megapascal. So average will be 75 megapascal. And if you compute the radius, which is the sigma x minus sigma average squared plus tau squared, here tau xy is 0 according to xy coordinate system. So you have 50 for sigma x and average is 75 as we just discussed. R becomes 25. Now because x represent to sigma x and minus tau xy coordinate, and y represent sigma y and tau xy coordinate, which is 100 and 0 and 50 and 0. So we can specify our x point here, our y point here. Now because x prime y prime axis is the axis rotated 20 degree counterclockwise, we consider 40 degree counterclockwise rotation of xy point in the Mohr circle, and it becomes x prime y prime coordinate. So x prime coordinate becomes sigma x prime minus tau x prime y prime, and what you can do is originally it was 75 and radius is 25, and if you take out 25 and cosine 40 degree, then you can get the reading sigma x prime. In the similar sense, if you do 25 multiplied by sine theta and take minus sign, you can obtain minus tau x prime y prime value, which is from minus 25 sine theta. So if you plug in cosine 40 and sine 40, it becomes 55.8 and minus 60.6, which means that tau x prime y prime will be 16.1 MPa, and the sigma x prime, which is the answer for the first question, will be 55.8 MPa. Okay, so this will be answer for A and B. Now the third question, problem C, gives us the material strength only, and it didn't give us information about pressure. So what we have to do is we have to express everything in terms of geometry: pressure P and radius R and thickness T. Of course, we can use R and T as 2 meter and 1 centimeter, but I prefer to use general expression for the normal stress. So let's try to express everything up here using in terms of PRT and try to obtain the answer for A and B in terms of PRT. So the average stress will be half of the these two normal stress, PR over 2T and PR over T, and it becomes 3 over 4 PR over T. Now the R, radius of the Mohr circle, becomes sigma x minus sigma average, which is PR over T minus 3 over 4 PR over T squared, and the tau xy is 0 due to the symmetry when we consider horizontal, longitudinal, and hoop direction as two principal axes. So it becomes PR over 40. This is the radius of the Mohr circle. Now, if you recall what we have done in previous page, the sigma x prime becomes sigma average minus radius of the Mohr circle cosine 40 degree, and tau x prime y prime is the radius of the Mohr circle multiplied by sine 40 degree. Okay, so you plug in the numbers, and it gives us PR over T 3 over 4, which is obtained from here, and R is 1 over 4 PR over T, and we have cosine 40 degree. And about tau x prime y prime, we have PR over 40, which is the radius multiplied by sine 40 degree. So here, after plug in R 2 meter and T 1 centimeter, it becomes 200. After replace R over T as 200, we obtain 111.7 P for sigma x prime and 32.14 P for tau x prime y prime. Now, after obtaining the sigma x prime and tau x prime y prime in terms of the internal pressure of the gas, we have to make sure that sigma x prime is smaller than allowable stress in normal direction, which is 125, and tau x prime y prime must be smaller than the allowable stress in shearing direction, which is 70 megapascal. So if you plug in 70 megapascal and 125 megapascal, because both conditions should be satisfied, we obtained P should be smaller than 1.12 megapascal and P should be smaller than 2.178 megapascal. Okay, so here what we obtained is that P must be smaller than 1.12 megapascal to satisfy both conditions, and that will be the answer for the third question. When the material strength is given, what will be the maximum pressure of gas that can be stored in this cylindrical pressure vessel? Okay, so with this, let me finish the recording of the first problem.